This is Kim. After a long day of ethical hacking and penetration testing, he just wants to relax and watch a movie. So, he opens his browser, types netflix.com, and hits enter. And just like that, the Netflix homepage appears. Fast, smooth, and seemingly effortless. In the last video, we saw that when Kim presses enter, the browser sends a request to the Netflix server. We also saw that this request follows a structure with 5 main parts: the request line, the host, the user agent, the referrer, a blank line, and often some cookies, as seen in the Burp Suite capture of the real Netflix request. So your browser sends this well-crafted letter to the server. But what does the server send back? It replies with a response, like a letter in return. Here's a basic example of what a response from the Netflix server might look like. Let's break it down, line by line. The first line is the status line. This is the server's way of saying, I got your request, and everything went fine. HTTP 1.1 is the version of the protocol being used. 200 OK is the status code. It means success. The server received the request, understood it, and responded without any problems. But not all responses are this friendly. Sometimes you get a 404, which means not found, the page doesn't exist. Or a 403, which means forbidden. You're not allowed to access that resource. We'll explore status codes in more detail in an upcoming video. The next line is the server info. This line tells us what software the web server is running. In this case, it's Nginx, version 1.15.8, a popular open source web server. For hackers, this tiny piece of information can be a clue. Different server software, or even different versions, may have known vulnerabilities. It's like the server accidentally telling you what kind of armor it's wearing, and sometimes where the cracks are. Then comes the date. This tells us exactly when the server sent the response, down to the second, in Greenwich Mean Time. It's like a timestamp on the response letter, proof of when it was written and sent. It may seem trivial, but this header can be very useful. For browsers, it helps with caching and knowing if a page is fresh or outdated. For developers, it's helpful when debugging time-based issues. And for hackers, the date is sometimes a clue about when a system was last updated or even synchronized. If the time is far off or wrong, it could suggest server misconfiguration or even that the system hasn't been updated in a while. For example, if you see a server still returning dates from 2018, it might be running outdated software, which could mean unpatched vulnerabilities are hiding underneath. It's a small detail, but in hacking, small details can open big doors. Next up is the content type. This tells the browser what kind of data it's about to receive, so it knows how to interpret it. In this case, it's saying, hey browser, I'm sending you text, but it's not just plain text, it's HTML, so render it like a web page. There are many other content types. For example, text CSS, which tells the browser, here's a style sheet, use it to style the page. Application JavaScript, which signals the browser to run a script. It says, I'm sending a script, run it in the page. Another common content type is image PNG, or video MP4. This let the browser know, here's a media file, display it or play it. So the content type helps define the browser's behavior, but it can also reveal security issues. For example, a page accidentally echoes this text. If the content type is text HTML, the browser interprets it as HTML and runs the script, which turns the page into a working cross-site scripting exploit. If it's text plain, the browser treats it as simple text and just displays it. So that single header, text HTML or text plain, can be the difference between a harmless page and a working cross-site scripting exploit. Now comes the content length. This header tells the browser how many bytes of data to expect in the body of the response. In this case, 98 bytes. It's like the server saying, heads up, I'm about to send you 98 bytes. If you get less, something went wrong. For browsers, this helps ensure the full response has been received. This is especially important when downloading files or streaming media. And finally, after all the headers, there's a blank line, and that's important. This blank line means I'm done sending headers. The rest is the actual content of the page you requested. This content is called the body of the response. In this case, a simple HTML web page. This is what your browser renders as a visible web page. And here's something cool. If you save just the body of the server's response as a file and open it in your browser, it still works. Why? Well, because that's exactly what your browser does behind the scenes. Let's see that in action with Kim. Kim opens a terminal and navigates to his Documents folder. There he creates a new HTML file named content.html using the Nano text editor. Inside it, he pastes the body of the server's response seen earlier. He saves it by pressing Ctrl-O, then Enter, and exits with Ctrl-X. He can then check that everything worked properly. Back in his File Explorer, Kim opens the Documents folder, then double-clicks on content.html. And just like that, the browser opens the file and renders it like a real web page. You can see the text, "Welcome to Netflix.com," right there on the screen. And at the top, the tab says Netflix. That's the title element inside the head tag. The head section is used for metadata, things like the page title, character encoding, linked style sheets, or scripts. It's not visible on the page itself, but it affects how the browser understands and displays the content. This little demo is a perfect example of what your browser does with an actual HTTP response. It reads the body of the response and checks the content type header to understand what kind of content it's dealing with. Then it renders that content visually, whether it's HTML, JSON, CSS, or something else. So everything you see in the browser, the text, layout, and images, comes from the response body. For hackers, this is where things get interesting. Sometimes the body can contain information never intended for users. Things like hidden comments, misconfigured pages, or exposed data can appear in the body, even developer notes or forgotten debug code. For example, an HTML comment saying, "Admin interface at secretadminpanel.php, restrict before launch." To a normal user, that's invisible in the browser. But to a hacker intercepting the response with a tool like Burp Suite, that's a lead, a big one. Other common leaks are API keys accidentally exposed in JavaScript, which can give direct access to internal services or sensitive resources. So, the body of the response is a treasure map, or a trap. Either way, ethical hackers read the body like a story. Now, let's see this in action. We'll follow Kim, who's using a web security tool called Burp Suite to capture and inspect a real HTTP response. If you're not familiar with Burp Suite, don't worry, I've got you covered. Just watch the video that appears above, where I explain what Burp Suite is step by step. In short, Burp Suite is a web proxy that lets you capture and inspect all browser traffic in detail. To get started, Kim opens the search bar on his computer and types Burp Suite. He clicks on the Burp Suite icon, and Burp Suite fires up. Once it opens, he goes to the Proxy tab, and then clicks on Open Browser. Burp's built-in browser launches. And here's the cool part. It's already pre-configured to send traffic through Burp Suite, so there's no setup needed. As we can see, the default Google page opens, and the HTTP History tab begins to fill up in real time. Every request and response is logged and waiting to be explored. Now, Kim types Netflix.com in the address bar and hits Enter. Burp quietly captures both the request his browser sends and the response the Netflix server sends back. In the HTTP history, Kim locates the entry for Netflix.com. Once he clicks on it, Burp Suite displays both the request and the response. The request is a standard GET request, just like we saw in the previous video. We immediately recognize the key elements: the request line, the host header, the user agent, and other familiar headers, like the accept language. Kim now clicks to view the response. And there it is, an actual HTTP response, captured live. Let's break it down line by line. The first line in the server's response is the status line. The status code 301 means the page has been moved permanently to a new location. Why does this happen? Well, because when Kim typed Netflix.com into the browser, it defaulted to http netflix.com, not HTTPS. So the server replies with, "Hey browser, you came through the wrong door. I've moved. Go here instead." The next line here is the location header. It tells the browser where to go next. In this case, it redirects Kim to HTTPS, the secure version. This is a common behavior on modern websites. Big sites like Netflix always force HTTPS to ensure encrypted, secure communication. Next is the content length, which is 0. This is because there is no actual content in the body, just headers. The server is saying, "I'm not sending you a page, just instructions to go somewhere else." That makes sense because in a 301 redirect, the only thing the browser needs is the new location. There's no need to waste bandwidth sending HTML. The VIA line reveals intermediate infrastructure, like proxies or load balancers. Here it says the traffic passed through a server in Europe West 1, likely AWS, in Ireland. The next two lines, XXSS protection and X content type options, are security headers. XXSS protection, also called X cross-site scripting protection, helps block reflected XSS attacks. X content type options prevents the browser from trying to guess the content type, which could be exploited. The next line, strict transport security, tells the browser, always use HTTPS for the next year and for every subdomain. This helps prevent SSL stripping attacks. If you don't know what all those attacks are, don't worry, we'll cover them in future videos. At the end of the response, we see several X-Netflix headers. These are custom headers used internally for debugging or, for example, to track how long the proxy took, here 12 milliseconds. So even when there's no visible page, a response like this is full of clues. A redirect, a server fingerprint, security policies. This is why hackers read every line, even in a 301 response like this one. So now you know, an HTTP response can either contain a full web page or just instructions and redirects. But in both cases, it often hides clues. A server fingerprint, a security header, or even a forgotten comment from a developer. To a hacker, it's never just a response. It's a conversation, and every line counts. So that's it for today. You've seen what a real HTTP response looks like, whether it's a full web page or just a silent redirect. We unpacked the headers, decoded the clues, and showed how even a boring 301 status code can reveal hidden insights. In the world of ethical hacking, every line tells a story, and this is just the beginning. If you enjoyed this deep dive, make sure to like, subscribe, and hit the bell so you don't miss the next episode. Bye-bye!